Okay, that's Krebs scabs. So this is what we're looking at overall then. So oxidative phosphorylation, this section here. Chemiosmosis, we've covered now link reaction, renew glycolysis. We've just done the Krebs cycle. Again, I don't expect you to know that off by heart when you come in, but that's one we just need to practice over and over again to get it clear in our head, so that ultimately you can write a 5-6 mark answer for it. We'll go now and have a quick look at electron transport chain. Okay, I'm going to skip that video for now because I think this is the easiest way to get your head around electron transport chain. What it is, it's a series of carrier molecules. Sometimes they're called cytochromes, but basically they're passing hydrogen and then electrons down a series of carriers, and in doing that, energy is released. If you have a look at this, this is the best way for me to remember it. If you imagine this is an increase in energy level up here, and what you've got is NADH coming in, which is a carrier with hydrogen attached to it. It's quite a high energy molecule with this hydrogen attached to it, and what it's doing is it's basically passing the hydrogen onto another hydrogen carrier. Again, you don't need to know all the names of them, but you do need to know that this second hydrogen carrier is at a lower energy level than the first one. So as that's passed down, I put this star here because enough energy effectively is released to pump 3 hydrogen ions into the intermembrane space. Now if we can get 3 hydrogen ions into the space, what can we make? 1 ATP. So I suppose each of those stars really is representative of enough energy to make 1 ATP. So, as I said earlier, NAD, higher energy level than this one. Energy is released there, so we can pump these 3 hydrogen ions in the membrane space. Again, the hydrogen is then passed down to this next carrier, and then at this point something different happens. The hydrogen is split. So you've got your hydrogen ion here, your proton effectively, because hydrogen, remember, is only made of 1 proton, 1 electron. It's split. So your hydrogen ion goes off, the electron is then passed down here to a lower energy level, and then passed again to a lower energy level, and to another lower energy level. And again, at each of these points here, enough energy is given out to pump 3 hydrogen ions in the intermembrane space, which is what's going on here, and therefore make 1 molecule of ATP. At the end of this, so here what we've got now is an electron carrier with an electron on it. It needs to get rid of that electron. And what does it do? Well, it adds it to oxygen. Oxygen has an affinity for electrons, so it will pick that electron up quite happily and it'll give it a negative charge. Now because it's got a negative charge, ultimately when these hydrogen ions here, they've gone through the intermembrane space, they've gone through ATPs and so on, we've got hydrogen ions with a positive charge. Well, opposites attract, don't they? So the positively charged hydrogen ion and a negatively charged oxygen ion attract, and so ultimately we form H2O, water. You'll sometimes see this, well, shown differently in the books because that doesn't balance, does it? 1 oxygen, 1 hydrogen doesn't make H2O. It doesn't work like that. So they often talk about it being half H2O and whatnot. But the concept is what you need to grasp. So it's oxygen that you've breathed in. That's the purpose of breathing. The oxygen you've breathed in accepts this electron, then joins to hydrogen, and ultimately that reaction forms water that you then breathe out. So the whole purpose in taking in oxygen is basically to soak up these electrons, turn it into water so you can then breathe it out. Okay, again, I'm not expecting you to have all this information stored in your minds ready for coming into the lesson, but a fair understanding of what it is we're looking at will go a long way. I think this is something you need to write out. Once you've got your head around the concept, that's the hard part, but then just remembering it so this can structure your answer is what we're aiming to do. And ultimately I need you to be able to link it to the whole of the process, so particularly that part there about the hydrogen ions and what is going on there, where they go, which you already know. They head off to chemiosmosis. Let me just pause that there. The thing I'm showing you at the minute is something that really there's always a lot of debate about. When you look in the textbooks, they're all slightly different. But one of the tasks that we'll do when you come into the lesson is working out how much ATP is used here in each of these processes and how much is made, and therefore what the net ATP gain is. You see different figures in different books, so if you do have the time, have a look, see if you can do a bit of research and see if you can figure it out. But we will spend a little bit of time. I'll make an activity that gets you to go through and count those up in the lesson. Okay, so back to the outcomes. These were the aims. So for A star, hopefully you can explain how hydrogen ions are moved into the intermembrane space. I've not explained exactly, but if you link to some of the things from last lesson, you know where the hydrogen ions now come from in the electron transport chain, and we mentioned the proton pump. You've now seen where the energy comes from to drive that proton pump to get the hydrogen ions into the intermembrane space. Obviously, it's the electron transport chain that provides that energy. Describing the Krebs cycle. So remembering the names of the key parts. So your acetyl coenzyme A, oxaloacetate, citrate, and then Krebs carbs 6544s. The dehydrogenations and the decarboxylations. And finally, recalling how ATP is made is building up on last lesson really, and looking at chemiosmosis and linking chemiosmosis to the rest of the process. And that's about it for today. There is just one more thing that's just popped into my head. So for each NAD that you've got coming into electron transport chain, how many ATP can you make? So if that's enough energy to put 3 hydrogen ions into the intermembrane space, you know that 3 hydrogen ions equals 1 ATP. So effectively, for each NAD, you get 1, 2, 3. Yeah. FAD that you saw in Krebs cycle, FAD feeds in here. So for each FAD, you only make 2 ATP. Okay. So every NAD, you're basically getting 3, 6, 9 hydrogen ions in the intermembrane space. For FAD, you're getting 6, which is the equivalent to 3 ATP for NAD, 2 ATP for FAD.